Hi, I'm Bruno, a researcher from INRIA. I represent our work on the user preference and performance using tagging and browsing for image labeling. Image labeling consists in associating images with a list of labels describing its features or the concepts it represents. Images are often labeled manually to categorize contents and easily navigate and retrieve it. Labels can also provide run-through data to train supervised machine learning algorithms. In this scenario, they are associated to areas of the images or video frames to provide more descriptive power. Producing run-through data is essential and can hardly be automated. A report from Cognitica Research estimates, for instance, this market to $4.1 billion in 2024. Manual labeling is also essential in scenarios that remain too challenging for automated approaches to provide precise results or give enough details based on a given ontology, which is often the case when analyzing sport sequences. Yet, labeling tasks remain tedious even when splitting up the work to crowd workers. These tasks are repetitive and last longer depending on the levels of details required. Thus, it remains important to study what factors impact the user performance to optimize it. Labeling is usually performed via two tasks. Tagging consists in assigning labels to a single image and associate them to an area if necessary, while browsing consists in focusing on a single label to assign to multiple images. The literature focuses almost exclusively on these two tasks, but there exist hybrid tasks combining the two approaches for which annotators select several images to assign multiple labels to, or vice versa. To consider all possible task variants, we study their underlying strategies. Let's say the annotator is facing 4 images that consist of 9 shapes each, and they must count the shapes for each image. They can assign all labels on a single image at a time, thus adopt an image-oriented strategy, which relates to a tagging task. Or they can assign a single label to multiple images, thus adopt a label-oriented strategy, which relates to a browsing task. We designed an abstract task to minimize the bias from expert knowledge one might have of natural images. Images consist of 9 geometric shapes that provide 3 visual complexity levels, inspired from the work of Dondery and Voff and Horowitz. The lowest level relies on colors, a non-pop-out feature, and the highest on high visual redundance. Annotators must count and annotate the number of each shape, excluding circles that act as distractors. There exist 3 label types, and annotators must select a value between 2 and 4 for each. They must select the right labels, then click on the corresponding image. In this case, the annotator adopts an image-oriented strategy. In this second case, the annotator focuses on a label type at a time, thus follows a label-oriented strategy. We identified 3 inherent factors to labeling tasks that likely impact the user performance but were not investigated to date. We vary the visual complexity and the number of images displayed at once from 1 to 9. We also vary the label persistence by enabling buttons to remain in the same state, thus facilitating selecting several images with the same label, or be switched off upon selecting images. We ran 2 experiments. The first focused on strategy users adopt when given the choice. It included 18 participants and focused on 3 dependent variables: the success rate, the task completion time, and the strategy scores. The second experiment focused on the strategy efficiency, included 24 participants and focused on the same dependent variables, excluding the strategy scores. We defined 2 metrics inspired from the work of Gogi and colleagues to assess the participant strategy. These metrics are computed over blocks of 9 images and only for blocks involving matrices of images larger than 1, as a single image forces an image-oriented strategy. They range from 0 to 1, 0 meaning the labeling actions did not follow the strategy, while 1 means they all did. We can represent the evolution of these scores through all blocks of the experiment. These participants had an image-oriented score of 1 for all blocks, meaning they performed all actions on a single image in a row and never came back to a previous image more than once. Their label-oriented score was always close to 0, meaning they kept switching from one label type to another. Here is an excerpt from their performance. In the second case, the scores changed drastically after a turning point. The image-oriented score averaging 0 means the participant came back to images previously visited regularly, and the label-oriented score topping at 1 means they mostly focused on a single label type at a time, as the following excerpt depicts. We aggregated data per participant and used error bars representing 95% bootstrapped confidence intervals. We used visual estimation techniques to estimate significant differences. The idea is that based on two data groups, we compute the mean of the differences between data points along with confidence intervals. The smaller the confidence intervals are and the larger the distance is to the zero line, the more evidence exists of a significant difference. All data are available online to support replication and reproducibility. We plotted the success rate based on each visual complexity levels. Plotting the mean of the differences indicates strong evidence of an impact of the visual complexity on the user performance. Similar plots with the task completion time lead to the same conclusion. We plotted the average scores over all blocks in function of the button persistence and found evidence that using persistent buttons nudge participants into using a label-oriented strategy. We identified user behaviors by plotting the evolution of the scores through the experiment and running a k-means algorithm on the difference between blocks. We found overall 4 behaviors. Half of the participants used the image-oriented strategy exclusively. 1 participant followed a fairly consistent strategy that evolved through time. 3 participants used an image-oriented strategy but switched transiently to the label-oriented strategy, and the rest of the participants adapted their strategies based on the task at hand. In the second experiment, we fixed the strategies and forced participants to use one or the other. For the image-oriented strategy, they had to select all label types before selecting an image. For the label-oriented strategy, they had to assign all images with the label type before accessing the next. We plotted the success rate and task completion time for both strategies. We found small evidence that using an image-oriented strategy leads to short labeling times. We looked further into possible interactions by plotting similar data for the 3 visual complexity levels and found evidence that this effect seems impactful for complex images. To summarize, we found evidence that half of the participants used an image-oriented strategy regardless of the experimental conditions, indicating that tagging tasks are preferred overall. Using persistent buttons seems to nudge participants into using a label-oriented strategy, as it facilitated going from one image to the next without clicking a button again. Hence, an image-oriented strategy produces shorter labeling times compared to a label-oriented strategy, especially when labeling complex images. Based on these results, we propose 3 design recommendations. Tagging tasks should be preferred when designing labeling tools. We recommend considering the visual complexity of images when designing labeling tools, as it seems to have an impact on the user performance. Finally, we observed more errors using persistent buttons in the first experiment, but not the second. These were likely mod errors, therefore designers should implement safeguards. Thank you for your attention.